everyone. Thank you for joining this session. I'm here to talk to you about some work we've been doing as part of a UK research project between Rigetti, HSBC, and the University of Edinburgh, where we really want to be able to bridge that gap, as we were hearing about earlier, between the kind of quantum algorithms that we hear promise of and practical and societal applications. So today I'm going to be talking to you a bit about financial crime, kind of laying the scene of why we actually care about financial crime, why it's a problem, getting into kind of what we've been trying to do technically to address this problem as a team, and then I'll be handing over to my collaborator Mattia to get into the work that we've been doing with Rigetti's quantum computers. Okay, that's the title. Cool. So why do we care about financial crime? And we've been hearing about, fraud detection, it's a potential use case of quantum computing. And I don't think it really hits home of like, why do we actually care about quantum machine learning or machine learning applications in general for financial crime use cases? So if we look at just some of the numbers, and this was some statistics that came out of the UK House of Lords on the left, and it's actually that fraud contributes to 41% of UK crime against individuals, with a total of $1.9 billion of loss in the UK alone. And HSBC is a primary bank for the UK, so you can imagine that it equates to a considerable amount of loss to our customers, to ourselves, but more importantly, this is money that's going away from individuals, you know, your grandmas, yourself, and going into the hands of criminals. So on the right-hand side, I think this is where I get most interested and passionate about. And this is anti-money laundering. It can also go into terrorist financing, sanction evasion. And the United Nations Office of Drugs and Crime recently reported that 2 to 5% of the global GDP, upwards of $2 trillion, is laundered money every year. And this is a very here and now problem. We think we have all these great AI, Gen AI applications, but this crime is still happening, right? And like last year in Singapore, there was a massive scandal around money laundering with 3 billion Singaporean dollars being laundered by Chinese nationals for gambling reasons and whatnot. And this actually caused a huge, huge fine for the bank that ended up being responsible for it. And only recently, in the last few days, they found that there was an internal employee, just a kid, who was under financial pressure, who was actually defrauding some of the onboarding that pervaded to this very large financial crime scandal. So this is a very real problem. This is something that's facing our society globally, and this is money that's going into the hands of criminals. So this is what we wanted to tackle. This is a societal problem that we posed to the UK government. So why do we think that we can actually do something with quantum machine learning? What makes fraud interesting for quantum machine learning? So actually, until very recently, most fraud detection systems were what we call rule-based, which means you have a bunch of really smart people, fraud analysts, who are trying to track the dynamics of financial crime, the dynamics of fraud, and implement rules that kind of are just decision trees that will stop a payment, right, whether or not it's fraudulent. But these tend to be kind of error-ridden. They're not able to catch the subtle patterns of criminal dynamics. And so you're always trying to update rules. You're always chasing the criminals who are a step ahead of you. And so recently, there's been a lot of movement to moving to machine learning models. And these are just your standard binary classification problems of being able to tell whether or not transaction is fraudulent or not. And what's interesting, as you move to these machine learning models, it's very quick. They're able to address these problems more rapidly. They are able to improve the fraud detection rates and things like that. But why would we want to look at QML? So what's interesting about fraud is very small improvements in detection capabilities actually, when scaled out across an organization, lead to pretty large numbers in fraud loss reduction, less cost to our customers, and also make the regulators quite happy, which if you know anything about banks, a lot of what we do is trying to make the regulators happy. So this is what we wanted to do. And this is where it was okay if we look at quantum machine learning and we see marginal improvements, we can actually take that and quantify that in terms of dollar numbers that we could save our customers by catching more crime. And so this is what we've been doing. So we decided to tackle this problem, and we have, through the Innovate UK, UKRI program, we developed a consortium, which is actually really interesting. And this was between HSBC, where I work, Rigetti Quantum Computing, the UK arm, as well as the University of Edinburgh and the NQCC. And each of these organizations have different strengths, right? The academic environment can go deep on fundamental research when it comes to quantum algorithms. Rigetti provides hardware accessibility, trying to kind of bridge that gap between academia and industry. And what I've been able to do with HSBC is actually really provide the business problem, like the real details of the specs that matter when it comes to doing something for the enterprise. And NQCC has been helping us in terms of potential commercialization paths. And I really like this because I'm actually an American. I've been involved in a lot of funding initiatives here in America. And this was something that I found very unique, and I'm very happy I got to participate in this research program within the UK, because it brings a large corporate enterprise customer with academia and a small startup to really tackle a societal problem. And I think, and what we're going to talk to you about today, is we made pretty good progress on this problem in the last couple years. So what I wanted to look at, and I'm going to be speaking for myself and the work that I did and what matters to me when I think about trying to apply quantum machine learning to financial crime, is what I wanted to actually make quantum machine learning commercially relevant. We see a lot of scaled down demonstrations, toy models, something that would never be used in production. And so I work with the business, the UK fraud team, to really understand what their technology requirements are at a very detailed level, so that when we're developing these types of solutions, we are able to actually push to what is something that could actually be brought into production. So if we look here, and maybe some of you are familiar with quantum machine learning papers with tiny little amounts of data, 10 to 20 qubits, that's not commercially relevant. So what we're looking at, these data sets have about 200 features, so 200 data columns, which if you do kind of a one-to-one mapping, that's 200 qubit simulation. But I think what's really important is the training data is 1.7 million data points. And so when we've seen these quantum machine learning papers are doing like 250 data points, 1,000 data points, we need to be able to scale this up, and we need to be able to manage millions and millions of transactions and inference, right? And another subtlety is that when you're dealing with a financial institution, the data is very highly restricted, especially around fraud. And so we can't just go willy-nilly sending data to quantum computers. We need to be able to bring the algorithm to the data, because it is very hard to move data around in a financial institution. So I felt like quantum computers were really not up to par to meet this task right now. And since I'm working for an organization, they want to see ROI. What can I actually do to deliver them something meaningful to their business? So this is some work that I did on developing a tensor network solution using tensor networks to simulate quantum circuits that is actually able to scale to meet all these business requirements, and actually has developed into production-grade software that the business is able to use today. So this is just a very quick highlight of what we've done. And something that I presented at NVIDIA GTC last year. And what I'm excited about is I was actually able to get some results out on real data on the fraud. So we were actually looking at how quantum machine learning would improve fraud capture for scam detection. So we had a data set associated with scams happening in the UK region. And in this plot, which is not necessarily what we're doing right now, but we are just comparing a quantum SVM against a classical SVM. And so this experimentation is really closely, tightly aligned with the business. Like, we are operating in their environment where the fraud data sits. So when we actually execute these algorithms, we're getting commercially relevant results. And also, if you take a look here on the x-axis, this is the number of features. So this is the size of the qubit simulation that we had done. So we were simulating 100 qubits using matrix product states and quantum feature maps. And we're actually able to go much farther than that. Because it turns out that these feature maps are not very strongly correlated. So we're able to scale up to the number of features that are actually relevant to the business and the money laundering teams. And when we looked at it compared to the baseline model, if you look on the y-axis here, this is the delta between the area under the curve, which is a metric that we can use to assess the discrimination quality of a classification model. And so if the if the line here is above 0, that means the quantum model is actually outperforming, in this case, a classical RBF model. And if it's below, that means the classical model is winning. And so there's a lot of ambiguity, right, about what kind of data sets we can use quantum machine learning for and when we're going to get an advantage. But in the case of doing something within a bank, you really just got to get down into the weeds and start testing it and see what you find. So where we're at now, just to kind of give a teaser, because this is like 6 months of work ago, we are actually able to use projected quantum features where we're actually using all of the features associated with the current transaction monitoring system, which is about 225. We're using all of the training data associated with their current production model, which is 1.7 million training data. And very interestingly, and this is a subtlety when you think about actually scoring fraud, is there's a really an inference time threshold, right? You don't want to be waiting around for a minute for your transaction to go through while you're like sitting at a CVS or some other store, right? And so there's a 40 millisecond cap on how fast inference has to be. And so we actually did a calculation, and we found that matrix product state simulations up to about 110 features are able to actually meet the real-time threshold with fraud. So at this point, this TensorNet, what I'm calling Tenfin AI, is at full production scale, and we're at a place where we're actually able to quantify in a commercial way, in a dollar value way, the impact that quantum machine learning can have against the production models today, which are in fact light GBM, XGBoost models, which are rather pervasive across the fraud industry. So I'm going to turn it over to my collaborator, Mattia from Rigetti, because as much as I've talked to you about the importance of fraud from a societal problem, why we want to investigate it, how we found that tensor networks are able to scale the solution, we're all here because we actually want to understand where quantum computers are going to play a role, right? And so Mattia will be talking to you a little bit more about when we go beyond this classically simulatable regime and we start actually using properties that we can only really get out of quantum computers, what benefit can we expect to see? So Mattia, I'll hand it to you. Thank you.
Perfect. Great talk, Mekena. Exactly what I'm going to talk about right now is how we improve on this by using a quantum computer and taking these benefits further. So really, here, the core of my talk is going to be about YQML. So which are the envisaged benefits of putting quantum in machine learning, and really this boils down to what advantage does QML offer over classical machine learning. Lastly, I'm going to show you a preview of how we intend to work closely with the project partner in the next few months in order to really take these envisaged quantum machine learning benefit and translate them into value by running on Rigetti quantum computers. Typically, for solving supervised learning problem, one has classical data. In this case, is financial transaction data. They get uploaded to a quantum computer. And a quantum computer, very generally, what it does is it transforms this data, map it to a quantum state, and then we extract information about the quantum state by sampling, either bit strings or crafting specific observables. This is a typical setup of, for example, quantum neural network, where the model is actually embedded on the quantum computer and trained there. In the case of quantum reservoir computing, where we apply nonlinear interaction, random nonlinear interaction to the input feature, and then the output is sent to linear layer, classical layer. And then lastly, the case of quantum kernel, which is probably the most relevant to us, where the input is mapped to a high-dimensional manifolds, and then the output is used to draw an upper plane that can separate the two classes. The details of this transformation don't matter, but what really matters are two key aspects of what comes out of the quantum computer. The first aspect is that the output here that is generated must not be classically simulatable, which means that there must not be a transformation that can be run solely on the classical computer and leads to the same output with a very good degree of approximation and using just a moderate amount of classical resources. That's the first crucial point. The second crucial point is that we want the output to be beneficial to the learning problem. This means that we can look at our model here and analyze things such as the bias and the variance trade-off, or the approximation power, the generalization power. And we need to be able to, in a way, connect some improvement of this important machine learning property with what the transformation is doing. So the work we have done focuses on the case of the discrete logarithm. It's a bit of a scientific problem, this one, but it's a problem where we know that classical computers cannot do well, while instead quantum computer can calculate this function efficiently. We can turn this problem into a classification problem and then downsample one of the classes, so it becomes an anomaly detection problem, very similar to what Mekena presented today. And the key aspect is that these transformations are not picked as is typically done in the literature with an inductive bias when it comes to the quantum calculation of the discrete logarithm, but they're just picked for the amount of quantum resources they are able to exploit. And I'll tell you what that means in a second. So this is the transformation we are, kind of transformation we are trying to implement. And the output on the transformation is then sent to a distance-based classifier, which is a very simple type of classifier, but we believe that this is the right choice under these circumstances to really highlight what's the impact of exploiting quantum resources at the feature transformation phase. What do we see here? What do we see here in this plot? So on the right-hand side, we see easy problem instances where we collected a lot of sample for the training set. On instead the other side, so the right-hand side of the slide, we see that we have the harder problem instances where we use very limited training data. The line represents, and on the y-axis, we have how we test how our classifier performs on the test set. And in particular, we are scoring the result using the area under the curve, which is a useful metric for imbalanced classification cases. What do we see here? So we're comparing three transformations: a classical baseline, which is a random Fourier feature, which is a type of classical formation that approximates surprisingly well wide classes of quantum circuit that are used in quantum machine learning. Then we have a quantum transformation that can generate a lot of entanglement and transforms the input towards states that are high-entangled states similar to the G8Z state, while instead the channel line, which is the most interesting one, transform our classical input data into states that have high magic. Magic is the key resource here. Why? Because magic is a computational resource that only quantum computers can generate efficiently. This is the key aspect. So what do we see? We see that as the difficulty of the problem increases as we move in this direction, the high magic states perform on an average metric over 10 problem instances consistently better compared to all the other transformations. And particularly, this classical transformation here has the worst performance. So this is what we want, because by mapping our input data to high magic circuit, we achieve the two aims that I discussed earlier, which is high magic means that we need a quantum computer to implement this transformation. This is not something that can be done classically efficiently. And also, high magic means high generalization power, which is something highly desirable for any machine learning model. So to conclude, in the next phase of the project, we will implement this on Rigetti quantum computer and with our partners, and we will go through this key step. So improve circuit design with moderate size problem instances, with large-scale simulation at the APCC cluster in Edinburgh. We will refine the use case with Mekena in order to try to make the scope more specific to something that hopefully fits better the stringent requirement of production case. And then lastly, we will gladly show you the results of our latest QPU generation, which is really at the heart of all we do at Rigetti. So thank you very much for your time, and let's see. I'll be happy to share more results in the coming months in 2025.
Thank you.